When an object falls to the ground, is it because Earth is pulling it down? Well, yes and no. In this video, we'll discuss how gravity works by looking at what happens when you drop an apple, why astronauts in orbit don't fall, and what would happen if Earth suddenly had twice the mass. And while it sounds kind of mystical, it's actually a scientific fact. Sir Isaac Newton described this concept in his law of universal gravitation. Planet X has a mass of 6 trillion kilograms, roughly the same as Earth's mass. Now, as we bring the bowling ball closer to the surface of Planet X, the gravitational force of each tiny cube on the ball becomes significant. At some point, the gravitational force of one of the cubes becomes greater than the gravitational force of all the other cubes. The sky would be just as blue, the birds would be just as chirpy, and the trees would be just as green. But after a while, strange things would start to happen. Instead, it's the difference in gravitational force between different parts of the planet that creates a net force, causing us to accelerate towards its center. We hope you enjoyed learning more about the science of gravity. If you did, please remember to like and subscribe for more fun science videos in the future. Until then, keep looking up. For example, the gravitational force of Earth prime on us would double. That means we would weigh twice as much as we do now. The extra weight would make it harder to walk, run, and jump. Would also affect our body functions, since many of them depend on the balance of forces inside and outside the body. For example, our blood pressure would increase due to the increased gravitational force. But the strangest thing about Earth prime is that it has a radius that's half the size of Earth's radius. That's because the mass of the planet doubled, but its volume didn't. To see how this would affect us, let's think about what happens to the gravitational force of Earth on us as we move away from its surface. According to Newton's law of universal gravitation, the gravitational force of Earth on us is inversely proportional to the square of the distance between our center and the center of the Earth. That means if we double the mass of Earth, we also need to double the distance between our center and the center of the Earth to keep the gravitational force the same. In other words, if we were to keep the mass of Earth the same, but double its radius, the gravitational force of Earth on us would become 4 times weaker. Since the radius of Earth prime is half of Earth's radius, the gravitational force of Earth prime on us would be 4 times greater than the gravitational force of Earth on us. That means if you weighed 100 pounds on Earth, you would weigh 400 pounds on Earth prime. The increased gravitational force would make it extremely difficult to move around. Walking would require superhuman strength. At that point, the bowling ball falls to the ground. Well, it depends on how high you can jump on Earth. You can jump up 1 meter on Earth. You would only be able to jump up 25 centimeters on Earth prime. And if you could jump 2 meters on Earth, you would only be able to jump 50 centimeters on Earth prime. In fact, you wouldn't even be able to hop like a frog on Earth prime. That's because the gravitational force of Earth prime on you would be so strong that it would prevent you from leaving the ground. You would be utterly crushed under the immense pressure. And unfortunately, Earth prime's gravity would not be gentle even in space. The gravitational force of Earth prime on us is inversely proportional to the square of the distance between our center and the center of Earth prime. That means if we double the distance, the gravitational force of Earth prime on us would become 4 times weaker. But since the radius of Earth prime is half the size of Earth's radius, the gravitational force of Earth prime on us would be 4 times greater than the gravitational force of Earth on us, even in space. So if you were an astronaut orbiting Earth, you would not be able to stay in orbit. You would simply crash into Earth prime. In other words, the bowling ball is pulled through Planet X when the gravitational force of one of the cubes becomes greater than the rest. But this doesn't mean that Planet X is pulling the bowling ball down. It's still the difference in gravitational force between the cubes that creates the net force. It's causing the ball to accelerate. But for simplicity's sake, we'll assume it's a perfect sphere. If we ignore the effects of air resistance and focus only on the gravitational force of Earth on us, we can say that we are in a constant state of free fall. Even though we don't feel like we're falling, we're accelerating towards the center of the Earth at approximately 9.8 meters per second squared. This is because the gravitational force of every part of the Earth on us is balanced, except for the parts that are directly beneath us. The gravitational force of those parts creates a net downward force that causes us to accelerate towards the center of the Earth. However, since the gravitational force of the parts beneath us is very evenly distributed, the acceleration we experience is almost uniform. As a result, if we're not paying attention, we don't feel like we're accelerating. However, If we were to dissect the Earth just like we did Planet X, we would eventually reach a point where the gravitational force of one part of the Earth on us becomes greater than the rest. At that point, we would experience a sudden increase in acceleration and plummet towards the center of the Earth. Fortunately, we never reach that point because the ground beneath our feet prevents the gravitational force of individual parts of the Earth from becoming greater than the rest. So when we say that the Earth pulls us down, we're really just talking about the effects of the net gravitational force acting on us near its surface. The Earth doesn't actually pull anything down, just that the gravitational force of the parts of the planet near you is greater than the gravitational force of the parts that are farther away. Place a test object, say a bowling ball, on the surface of Planet X due to Newton's law of universal gravitation. Every part of Planet X exerts an attractive force on the bowling ball. The portion of Planet X that is closer to the bowling ball exerts a greater gravitational force than the parts that are farther away. Since the planet is a sphere, these forces balance out in all directions except for the one pointing towards the center of the planet. Therefore, the net gravitational force acting on the bowling ball is directed towards the center of Planet X. So the bowling ball accelerates towards the center until it hits the other side of the planet and comes to rest. But this doesn't mean that the bowling ball is pulled through Planet X. The only reason it accelerates is because there is a net force acting on it. If we were to dissect Planet X into smaller pieces, we would find that the gravitational force of each piece on the bowling ball is balanced by the gravitational force of the other parts of the planet except for the closest one. The closest part exerts a slightly stronger gravitational force than the others, which creates an imbalance in the forces and causes the bowling ball to accelerate. Also, we can say that the bowling ball is not pulled through Planet X. Instead, it's the difference in gravitational force between different parts of the planet that creates a net force, causing the ball to accelerate. He said every particle of matter in the universe attracts every other particle with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. That means that if you take two objects and increase the mass of one of them, the gravitational attraction between the two will increase. If you move the objects closer together, the gravitational attraction between them will also increase. This is what holds planets in orbit around the sun and keeps our feet glued to the ground. If you want to know more about the nitty-gritty of how gravity works, keep watching. After all, the ground beneath our feet isn't really that far from the center of the Earth. That's a great question, and the answer lies in the way we define what we mean by the Earth pulling something down. You see, when we say the Earth pulls things towards it, we're really talking about the effects of the net gravitational force acting on an object near its surface. And the gravitational force isn't just coming from the ground beneath your feet. Every part of the planet is exerting a gravitational force on you. But it's the net force that determines whether or not you fall through the Earth. You may have heard that everything is attracted to everything else. But if the Earth is pulling down on us all the time, why don't we just fall through it? To illustrate this, imagine a spherical planet without any atmosphere or surface features like mountains or valleys. We'll call this Planet X. But what if we were to dissect Planet X even further? What if we divided it into tiny cubes, just a meter wide? So what does this mean for us humans? Now let's look at what would happen if the Earth suddenly doubled in mass. Let's call the new planet Earth Prime. Everything would seem normal at first. What would happen if you tried to jump on Earth Prime? So there you have it, folks. The Earth doesn't actually pull us down.